In this problem, we're going to calculate the heat that's delivered to a high temperature reservoir if we run a Carnot heat engine in reverse, so it's a Carnot heat pump. And when we're doing that, now we're supplying work, and so we're supplying 500 kilojoules. And what that accomplishes, we transfer heat from the low temperature reservoir to a high temperature reservoir. And so this QC is a positive number because our system is the heat pump. This QH is a negative number, and the temperature inside the cycle, the low temperature is 250 Kelvin, and the high temperature is 300 Kelvin. So what we're going to do is apply the second law and say this is a reversible heat engine, so delta S is 0. And since it's reversible, the entropy change is the heat transferred over the temperature, high temperature, plus the heat transferred, low temperature, over that low temperature. And this then becomes QH over 300, and this is QC over 250, and that equals 0. We can also apply the first law to the heat pump. So this is running continuously, so there's no energy change in the heat pump. It's at steady state. So energy is 0. It's QC plus QH plus W adds up to 0. So what we're going to do is combine these two equations. Well, let's solve for QC first. So QH then is equal to minus QC plus W. We'll substitute that back in here. So I made the substitution for work of 500, rearranged the equation. So now I can solve for QC. Once I have QC, then I can get QH from this equation. So QH is minus 2,500 plus the 500 for the work. So QH is minus 3,000 kilojoules. So this means we can put in 500 kilojoules of work and then transfer 3,000 kilojoules to the high temperature reservoir. So you can see this is a very efficient way to heat a house, for example, by using electricity. Instead of an electric heater, we can use a heat pump and be much more efficient. We can also calculate a coefficient of performance, which is something normally we do for refrigerators, since this is also a refrigerating system, depending on how we want to use it. And that's QC, what we're desiring to do, over what we have to put in, or we would have to pay for, if you like. So that's 2,500 over 500. So coefficient of performance is 5. Keep in mind this is ideal system, the real system. There's temperature differences between the temperature 250, for example, in the cycle, and the temperature of low temperature reservoir, likewise for the high temperature reservoir.